Welcome to the Nanovation podcast. Information about this and other episodes can be found at fillerlab.com/nanovation. If you like what you hear, be sure to tell a friend or leave a review at Apple Podcasts. It really does help. I welcome your thoughts and suggestions. You can contact me on Twitter at Michael Filler or via email at nanovationpodcast@gmail.com.
Grandma's recipe, right? You may know what it tastes like, but you may be able to see the pie, but actually how it's made gets lost when grandma doesn't pass it down to the next generation. So there are lots of recipes, processes that get lost through a lack of curation.
That's Matthew Realff, my colleague from Georgia Tech, talking about the fleeting nature of processes, the strategies by which a series of steps are organized and executed. In this episode of the Nanovation podcast, Matthew and I provide a sneak peek at an article we've been writing about something we call fundamental process innovation. We discuss what is and is not fundamental process innovation, and we explain why it is often unrecognized. We then present a framework to better understand it. We show that new areas of science emerge from it, and we even offer suggestions for nurturing it in the future. Our goal is to begin a dialogue among scientists, technologists, policymakers, and anyone else about how we can best accelerate such innovations in the future. This is the Nanovation Podcast, an exploration of big innovations emerging from small things. I'm Mike Filler, your host and a professor at the Georgia Institute of Technology. Enjoy the show. So it's a real pleasure to have Matthew Realff back on the show today. He's a professor and the David Wong Senior Fellow in the School of Chemical and Biomolecular Engineering here at Georgia Tech. He is the editor-in-chief of a brand new journal from the American Institute of Chemical Engineers. It is the Journal of Advanced Manufacturing and Processing. And he's here today to give the listeners a sneak peek of an article he and I have been writing over the last couple of years. And we'll get to that in a minute. But first, welcome back, Matthew.
Thank you very much, Mike.
Why don't you tell everyone what this new journal is all about?
Oh, I'd be happy to. So, as the editor-in-chief of this journal, I'm excited to say that what we're trying to do is to connect science and engineering advances to societal metrics. So, if you like to think of what we're trying to do with climate change, we're trying to connect metrics like CO2 concentration in the atmosphere to what we're doing with processes and manufacturing. In other words, how can we improve these metrics through using advanced manufacturing and processing? Now, I give you the example of an environmental metric, but we're also interested, for example, in human health metrics. So how can we connect advanced manufacturing, say, of cells or tissues or advanced biologics to human health outcomes? So not just looking at the scientific advance and how it changes the fundamental properties of a cell, but how do you then translate that into something that affects society through manufacturing and processing? So it's connecting science and engineering advances to metrics that are important to us as society. And we've done that really through partnering with institutes like Manufacturing USA, which is part of the DOE and the federal government's push to fund advanced manufacturing. So there are institutes like RAPID from the AICHE, which is focused on process intensification and process modularization. And we would like to see the researchers that are participating in these manufacturing institutes as our core group of authors and readers.
So can you explain how you end up connecting the manufacturing to these very important yet large outcomes like CO2 concentration in the atmosphere?
Yes. So that's the idea, that the authors of articles will attempt to bridge that gap. So,
so the how you connect it also.
Yes. So for example, we would like articles that connect how you can use natural systems to lower nitrogen concentrations, say NOx, by their action on the ground or their action on the atmosphere. They can actually pull certain species out of the air or out of the groundwater. So, trees, plants can both affect the CO2 concentration, and they can affect groundwater levels of particular components as well. And so how would you design a industrial ecological system to improve overall environmental quality, for example? So we have an article in the first issue that really addresses that particular concern. How do you, for example, design textile dyeing processes so that they lower their overall carbon and water footprints? So if you think, for example, of the advances in carpet manufacturing, we've gone from using Beck dyeing with high concentrations of acid dyes dispersed in hot water to actually adding pigmented dyes in small capsules to the fiber during the fiber manufacturing process, thereby completely eliminating Beck dyeing from some carpet manufacturing processes. That lowers the overall environmental footprint substantially because of avoiding that very energy and water intensive and waste treatment intensive step at the end of the processing.
For those who may not be aware, Georgia is one of the largest producers of carpet in the world, correct?
Yes, so 75% of U.S. carpet is actually manufactured within 50 miles of one town in the state of Georgia, which is Dalton, Georgia. And so all of the major carpet mills have their presence in that area, and the infrastructure to support them has also arisen around Dalton, Georgia. So yes, it's a very important industry for Georgia, which is one of the reasons why I happen to have focused on that over my career. And it turns out, again, in the first issue of this Journal of Advanced Manufacturing and Processing, we have an article examining the carbon footprint of 5 different carpet dyeing processes.
So seems like a very important thing to connect manufacturing to these kinds of important metrics. It seems to me, though, that people must have been doing this in the past, and that is the journal now a way to be a clearinghouse for these kinds of studies, to bring this community together in a way that it never has been before? Is that the idea?
Yeah, the idea is the journal will serve as a community nucleating point for people to study these aspects across different manufacturing systems and not one particular field or another. The other thing is that I think we've done a very good job on focusing on your classic metrics of cost, efficiency, energy use, etc. But we maybe haven't connected to other metrics that are important to us, and how the manufacturing system affects those metrics. And the example there being human health. Both from the perspective of the possible negative impacts of manufacturing on human health, but also the positive impacts that we can have by more effective manufacturing of advanced medical treatments. For example, again, if we want to use personalized medicine, we're going to have to figure out how to effectively take cells from people, culture them, grow them, quality control them, and then put them back into the right person. So that control of that...
I hope picking the right person is the easy part.
Yes, so do I. But it's interesting. Do you have to move the patient near to the manufacturing facility? so that you can get the cells from them. And if the first batch fails, you can go get a second batch of cells. And the shorter the distances, the better the manufacturing, because of the time lag and the cell growth and making sure you can maintain the environment so that the cells remain viable. So there's some interesting aspects of how do you design the supply chain? Do you distribute the manufacturing to the patient, or do you bring the patient to the manufacturing?
Right. I can see lots of hospitals connected to factories in my head now.
Yes, that's right, because factories will become an important component of this overall supply chain, and how you supply and how many suppliers there are of some of these important components is actually quite surprising. You might find there's only one.
Right. At Georgia Tech, we have an engineering research center. I forget what it's called right now, where their main goal is to figure out a lot of these questions around cell manufacturing, right? How you would take your cells, culture your cells, modify your cells, and put them back into your body. So that's exciting, I think. I invited Matthew here, as I mentioned at the top of the show, to give a sneak peek on an article he and I have been writing. The article is titled 7 Process Innovations That Changed the World. So we'll get to that in a second, but it is part of a line of thinking that's been happening within the School of Chemical and Biomolecular Engineering here at Georgia Tech. That includes myself, Matthew, my colleagues Victor Breedveld and Sven Behrens, around the idea of process innovation for nanotechnology. And in this article that Matthew and I have been working on more broadly, I think we realize that this is a important topic outside of nanotechnology. But for me, at least, it emerged from thinking about nanoscience and nanotechnology. So if you want to go back and kind of see the genesis of these ideas, you can check out episode 14, where Matthew talked about the chemical engineeringification of nanomaterials manufacturing with me. That's where this started, and that was about 2 years ago. Victor Breedveld came on the show in episode 37, where we reviewed a different article called Process Principles for Large-Scale Nanomanufacturing. I think that in part came out of these earlier discussions. And then the article today zooms out even a bit further and looks at process innovations for all types of manufacturing. And so we won't talk a ton about nano, but I want listeners to be thinking that these concepts are really relevant to nano. So let's start by thinking about how we perceive technological innovation today. Matthew, can you talk about the usual route, or at least the route people think about when they think about technological innovation?
Yes. So we tend to think that scientists in the lab are working on advanced discoveries, and that those advanced discoveries reach a certain level of maturity, and then they make their way out of the lab and become innovations in products. And so we think a lot of innovation happens around widgets that embody the scientific principles that have been uncovered as part of the discovery process.
So it's basically fundamental science and discovery leads to translation from the lab into a commercial technology.
Yes, right. That's a good summary.
That's my job as the host, is to try and summarize what the guest says.
Good.
If you listen to all the best hosts, they do a good summary. So we're here to say that we don't necessarily think that is the only way at which technological innovation happens. And we wanted to talk about how we view and think process innovation leads to significant technological innovation. So before we can get to this process innovation piece and talk about why it's important and why it's even overlooked and that the hidden nature of it becomes problematic, let's talk about what a process is. What's a process, Matthew?
So for me, a process is essentially a series of steps which enables you to transform the initial starting material, say, for example, a piece of metal, into the final manufactured object. So we have drilling holes, we have bending the metal, we have assembling parts. All of those are steps in the overall process to create the product from the raw materials.
So like if we think of making a car, right, and the assembly line, the process is all those steps, and you can watch these videos on YouTube, from metal to a chassis to adding doors and the engine. What are those steps, and what is their sequence?
Yes, that's a process.
Okay. So then what's process innovation?
So process innovation is really understanding how changing the order of the steps, combining steps, dividing steps, and then how a new particular manufacturing step itself impacts the overall flow of the product through the process. And so we see, for example, in the context of making steam, that you might have a situation where you heat the vessel up, make the steam, move the steam into another vessel, and then condense the steam in that vessel and cool the original vessel back down. So in that sequence, you can have all the cooling and heating take place in one vessel, or you could have the cooling and heating take place in different vessels, and you would potentially have different outcomes by the way you factor those steps between the different locations.
Okay, so we have a couple other really great iconic examples of process innovation, but before we get to those, I think it's important to talk about why we think process innovation is not basically paid attention to enough, and that's because it's hidden. Can you describe what makes process innovation hidden?
Yeah, so I think it's interesting if we examine history to understand how we refer to ages. So we refer to the Stone Age, the Bronze Age, the Iron Age, and in each of those cases, we're referring to the material, the outcome of a process that transformed the ore into the actual product itself. And so in history, what leaves its mark are the products, the arrowheads, the swords, the chainmail. These are the objects we have, rather than actually the process that led to their actual fabrication. And so processes get lost. They disappear because they don't leave their mark in a concrete way.
Yeah, and I think that is really profound, that they're so ephemeral. You gave me the example the other day of the Romans making concrete, right? And then we knew how to do it. They had a process for making concrete. You can go see the structures that they built. But then there was a period of time where everyone kind of forgot. It was lost to history, that the process, even though they could go, if you existed on this planet, let's say 1,000 years ago, you could go see the structures, but you didn't know how to make the structures because the process was so ephemeral and the ideas were lost.
That's right. And I think there are situations where people, your favorite grandma's recipe, right? You may know what it tastes like, right, but you may be able to see the pie, but actually how it's made gets lost when grandma doesn't pass it down to the next generation.
Right.
So there are lots of recipes, processes that get lost through a lack of curation.
Another thing is, another related thing to talk about is that the product, the thing you can see, embeds the process. But people, as you pointed out, see the product.
Right.
You're looking at the product, you can't see how it was built per se.
Right. And there are actually products that really are processes. So, for example, the internal combustion engine, that's a process to turn gasoline into power, but no one talks about the internal combustion process. They talk about the internal combustion engine, because that's the thing we can see, that's the thing that we can touch, but it's really embodying the conversion process, and that's what makes it valuable to us.
Okay, so that's why they're hidden. You call that kind of the iceberg problem of process innovation. Let's go even further back than the internal combustion engine, and talk this great example from the 16th century, where the Venetians figured out how to build ships by changing the process by which ships were built. Can you describe what they realized and what it did for them?
Yeah, so there is a situation where the Mediterranean is a very important hub of commerce and a need to protect commerce for long periods of time. And so the Venetians discovered that if they took ships and actually figured out how to standardize and modularize them, that they could have the ship float down a canal and have different artisans specialized in making the particular pieces of the ship, then go and fit those onto the ship and increase the production rate of ships tremendously because of this innovation of standardizing the parts and modularizing the construction so that they could effectively factor the production of the ship into a set of different steps, which all the ships would go through as they floated down the channel. And what that did was it increased the reproducibility of the ship making. It increased the productivity of the workers and allowed the Venetians to effectively have naval dominance of their area of the Mediterranean for a number of at least 1 or 2 centuries.
So there's two key things I want to pull out of that. One is the canal is basically an assembly line, right? So we give a lot of credit to Henry Ford for the assembly line in automobile manufacturing, but that certainly was not the beginning of assembly lines. And the other thing is, what Matthew's describing is this idea of translating from a few artisans building the whole ship, right, to every artisan having one job and standard parts that they then, as the ship came down the canal, that one person did that one thing. They inserted that bolt, if you will, or cut that plank and inserted that plank, versus that group of artisans together and only a couple of them putting every bolt, every plank, and doing every component of the ship. And that brought tremendous efficiencies.
Yes.
Another one I love from kind of today's world that listeners will recognize immediately is that of shopping.
Right. So there we again have gone from a situation where the shopkeeper would be pulling items off of shelves behind the counter and handing them to the customer, or placing them on the counter to put together in a bag to hand to the customer, to a situation where the customer themselves is moving with a shopping cart down aisles and collecting the items for themselves and then going to a checkout and paying for the items. So again, what's done there is that the steps of collecting the items and putting them in a basket has been separated from the act of paying, whereas the shopkeeper was kind of combining those two actions into one. Once the items were assembled into the package that the customer wanted, he would then hand the customer the items and the customer would pay for them. Now those two are separated, and the customers can in parallel explore the shopping aisles and put together their items and then effectively be processed through the payment system in a more efficient fashion.
And so you can view this one way, which is this is much worse for the customer, right? Now they have to traverse the aisles and walk around with the shopping cart versus just handing a list to someone and letting them do the work. But the efficiency gains and the cost reductions, because now you need many fewer people to serve many more people, just outweighed that cost, right? And it really improved the economics of shopping.
And increased the size of shops that you were able to have, because, again, you could have multiple aisles, which increased the choice that the customer has. And now, of course, we've seen, the next level of evolution of this idea where, you don't have the shop itself as a physical place, but is now a virtual place on the internet where the number of items can be multiplied by at least another 1 or 2 orders of magnitude. And the customer, again, has the shopping cart, but now instead of moving around the aisles, is moving a mouse around web pages and is able to fill up their virtual shopping cart. And we've changed the logistics by which the customer no longer takes the items, puts them in their car and drives them home, but actually has the items delivered to the home instead.
And I think what is also, beyond that example just being really interesting, is the ephemerality of the shopping process right there. You wouldn't have recognized it as a change in process if you weren't really paying attention. Right, and that goes back to this iceberg issue and why we think process innovation of this type doesn't get the attention it deserves. Okay, so let's talk about how process innovation happens. We've given some iconic examples, not entirely from a manufacturing context, and we want to switch over and kind of push into manufacturing here. So I'm going to go through a list of ways in which process innovation happens, and then we will, through examples, talk about those different mechanisms. So in this article we've been writing, we have created a number of what we call schema, or mechanisms, by which process innovation happens. And those are parallelization, splitting of process steps, or splitting of flows of material, merging of flows of material, separating, then combining steps, splitting steps apart, and then subtractive manufacturing methods versus additive manufacturing methods. And I think it may be a little too much to swallow that list I just gave you, but I also think trying to describe each one, it doesn't help much either. And the best thing we can do is now go and give some examples and maybe talk about our 7 process innovations that change the world, and bring up in a couple of those cases how these schema were used in each of those innovations. So why don't we jump to that? So Matthew and I created a list of, as I've been saying, 7 process innovations, and we took them intentionally from the last 250 years, which is when there was this veritable explosion of innovation in manufacturing. And these are not the only process innovations that shaped the modern world or changed the world, but we think it's hard to argue that they weren't really important. I said this a minute ago. There's lots of process innovation that happens in information technology, in logistics, in financial transactions, and transportation. So it's really broad-based, but this article we've been writing, because of our respective interests, is in manufacturing. So our innovations are in manufacturing. So let's start with the first one, which is the earliest one. So we go in sequence from earliest to latest, and that is the Watt process for power generation.
Right. And so here again, we're faced with this nomenclature where we would say it's the Watt engine, whereas really it's the Watt process for making power. So early on in the coal mines in England, as they started to dig deeper and recover coal seams that were deeper in the ground, they obviously started to get below the water table and would need to pump the water out of the mines. And in fact, the Newcomen engine was the sort of first way in which this was done, where effectively by pulling a vacuum, you were able to suck the water up out of of a mine. And the way that was done was essentially steam was produced in a single vessel, and then that steam was condensed by cooling the vessel down, and that pulled the vacuum.
Right.
And what realized was that if you actually factored those two steps, so you effectively had the steam pass into a vessel and the vacuum was pulled without having to cool the same vessel down, that would be much more efficient. And so he factored the steam production from the vacuum pulling. And as a result, the efficiency of the engine was dramatically increased because you didn't have to cool and heat the same vessel, which, because it needed to contain the vacuum, was relatively thick in terms of its vessel walls. And so that's one of the reasons why you're able, in fact, to get greater efficiency. And with that greater efficiency came, first of all, the ability to pump more water, so therefore you could have deeper mines, but also you're able to reduce the size of the engine or the size of the process embodied in the engine. And then you could actually think about carrying the coal with the engine and moving the engine and the coal together, which leads effectively to railways. And so what we see then is then the explosion of the use of the steam engine beyond the actual coal mine itself, because you can have mobile steam engines and you can use steam engines to bring coal to engines that are located further from the mine. And that obviously underlies a lot of the industrial revolution that took place in England in the late 18th century.
What Matthew just said is that the early engines were so inefficient, they couldn't leave the source of fuel, which was the mine itself. So when they got, let's say, 10x more efficient with the Watt engine, not only did they become more compact, but you could actually carry enough fuel with you, as Matthew was pointing out. So it could leave. You could put it on rails. That's just, I love that example. It's so profound, and I think someone wrongly could look at what Watt did and say, it's just engineering, right? Which is a thing I hear a lot. It's just engineering. That is really profound in what it enabled, but then also it got to the point where this drove new science, right? Thermodynamics, needing to understand now really well how these engines were operating and how to make them as efficient as possible, was in large part driven by these innovations. And so I think this is a beautiful first example of how a innovation in process went backwards relative to the way we're used to thinking about technological innovation. It wasn't, in this case, scientific discovery that drove Watt to create the engine. We wanted more efficient engines to work at mines, but then that drove science to make the engine more efficient, etc. And I think that's really important to realize. So let's jump to another one of my favorite of the 7. I'm going to skip one, which is continuous paper making, which you all can read about when the article comes out. But I want to jump to the Bessemer process for steel manufacturing. So what was Bessemer, and what did he do?
So Henry Bessemer was an Englishman who actually...
Well, of course it was an Englishman.
Some of the early ones we picked also because of a slight cultural bias, I suspect, as well.
You don't know Matthew's English.
So he basically discovered that in making steel... the counterintuitively that blowing air through the steel would actually lead to increasing its temperature, because there were impurities in the pig iron that was being converted to steel, such as carbon, that would convert to carbon dioxide and leave in the gas phase. But at the same time, burning carbon to carbon dioxide creates a lot of energy, and so it would raise the temperature of the steel, and that actually allowed then other impurities to be oxidized, and those, some left in the gas phase, and some actually floated to the top of the steel and became the slag phase on top of the steel phase again, enabling them to be separated from the steel. So what he was doing was discovering an innovation in the process step, and at the same time he found that he couldn't control the level of impurity that was left in the steel very easily, and so the first 2 times he tried to license his discovery out, it actually failed. So he brought it back in-house and realized that what he needed to do was to completely remove the impurities, i.e. to completely separate the impurities from the steel, and then add those impurities back at the appropriate quantities to be able to control the properties of the steel. And this strategy, this process innovation of completely separating and then back mixing has become very ubiquitous actually in manufacturing processes such as for example gasoline or diesel, where we separate into different fractions and then blend those fractions back together to create the appropriate properties for diesel and gasoline. And I think there are other examples as well in manufacturing where that's done.
Okay, so that's an example of the separation schema, and also the combination schema, this idea that heating with a flow of gas and combining these two, where you're flowing this gas and creating reactions that are exothermic and creating more heat, drove the temperature higher and helped you in the separation.
Yes.
And that it basically provided a key route to steel for the railroad.
Right. And so now, again, we see these process innovations building on themselves. So you have the ability to move more goods on steel rails than you did on the previous generation of rails, because the weight of the engine and of the cargo could be much higher, and that then led to the ability to move goods further. Moving goods further meant that you could have the agricultural production further away to feed the city, and the cities could grow larger because of the ability to move food into them longer distances. And so in some ways, the sort of societal innovation of urbanization rests on our ability to have movement of goods long distances.
So remarkably profound innovation, getting from pig iron to better quality steel, all the way to building of cities.
And skyscrapers.
And skyscrapers, right. I think all of these innovations have this kind of knock-on effect characteristic, and after we go through a couple more of them, we'll kind of point out some of these key characteristics of process innovations. The next one I want to talk about is the catalytic cracking of crude oil, which is how for a long time we made gasoline and other kinds of fuels.
So this is another one that is very close to Mike and I's heart because it's coming from chemical engineering. But essentially, we had started to make fuels from crude oil, and we were doing so by separating the components out of crude oil. And we discovered that we would be better if we could use more of the heavier parts of the crude oil barrel by cracking them to make the molecules smaller. And so there were batch processes that enabled this to happen using, in fact, some of the early generations of catalysts. And we were starting to make progress in that field, but were held back by the fact that as you break the molecules apart, sometimes you're going to form coke, carbon, and that will foul the catalyst, and you'll have to shut the whole operation down, and that then makes you less efficient. And so what Eugene Houdry discovered was, in fact, that you could factor the regeneration of the catalyst, that is, turning it back into an active catalyst, from the place where the catalyst was being used to produce the fuel. And so he created a situation where you moved the catalyst in buckets between a regeneration vessel and a process vessel, and thereby made the production of the gasoline or the diesel or the fuel more efficient. Not only that, but the advances within the catalyst itself also meant that the molecules you were making had higher octane numbers relative to the sort of straight-run gasoline you would produce just by distilling crude oil. And it turns out that particular feature was very important in the late 1930s and particularly in 1940, when the RAF needed effectively to use fewer aircraft to defeat a larger Luftwaffe, and were able to have more powerful aircraft engines because they had higher octane gasoline produced through the Houdry process that actually gave them much greater lift and range on the aircraft than they would have had through the straight-run gasoline. And so this is a process innovation that it had a very profound impact on fighting a war.
And the scale up, the rate at which this was adopted was remarkably fast, right? And it, well, okay, so I should stop there and say, in a parallel effort, this was not so much Houdry, but a very similar idea was the idea of what we call fluid catalytic cracking. So as Matthew described, Houdry had this conveyor of catalyst, spent catalyst getting sent to a regenerator, which then on another conveyor sent back fresh catalyst or regenerated catalyst. Fluid catalytic cracking is where you take a flow of the reactant species, the oil you're cracking, and the flow fluidizes these catalyst particles. So imagine blowing air, let's say it's not air in this case, but imagine blowing air through a bed of sand vertically. The sand actually starts to move and dance. That's called fluidization. And not only was that a really great process because it gives you very efficient mixing, so you get very uniform temperature and pressures in these kinds of reactors, but then you could easily, effectively push out this catalyst into another vessel, regenerate it, and then send it back into the fluidized bed, the reactor portion. And so just by having the fluidization, it made the catalyst more easy to push around. It was behaving like a fluid. And that was a parallel innovation and ultimately then overtook Houdry's kind of conveyor approach. This interesting statistic that FCC, the fluid catalytic version, was first deployed in 1942, and within a couple years, by the end of World War II, so 1945, let's say 3 years, the capacity exceeded 500,000 barrels per day. 20 different companies were using it, and there were 34 of these such FCC units in operation in the United States alone.
Right, and the other aspect of that is the FCC was invented at MIT, and
you got to bring MIT in.
I had to bring it in. Yes, is that people literally didn't believe that solids would behave like fluids if you were able to blow gas through them with sufficient velocity. And so the whole science of fluidization was actually sort of created out of these kinds of process innovations, because now we had to understand how solids would behave as we blew these gases through them, and that led to a whole host of advances in the science of fluidization.
And even more broadly than that, you zoom out further, and it's not fluidization; it's particles and gas flows, right? So there's a whole several decades of science on understanding particles in a gas, maybe for fluidization, maybe for aerosols in the atmosphere, what have you. But it was driven by this realization through the FCC process that it was even possible.
Right.
Okay, I want to do. I'm going to do two more. We're having so much fun talking about this, but I don't want this episode to go on for 5 hours. I'm going to jump to the planar process. The planar process for integrated circuit manufacturing. And since this is my area of interest, I'm going to go ahead and take this. And Matthew's been doing a great job, so I want to commend him on that. But so how do we build integrated circuits? There is a method that was developed in the 1950s at Fairchild Semiconductor called the planar process. And actually, if you want to learn more about Fairchild Semiconductor, you can listen to Dennis Hess, and we'll put this link in the show notes, on an earlier episode of Nanovation where we went through the discoveries that happened at Fairchild in a lot of detail. But basically what they realized was a way to make the transistors of the day operate much better was to embed them inside a silicon wafer. So that was a discovery by one of the employees there, Jean Erny, and he was able to develop a process. He called it the planar process, and the transistors that were produced from it, because they were now protected from the environment, they were inside of the silicon instead of on top of the silicon, were impressive. But there was another thing that was realized by Robert Noyce. Robert Noyce was one of the founders of Intel, if you know that name. He realized that now that all the transistors were inside the silicon, the top surface was flat. And that made it much easier to now interconnect multiple devices, right? So before this point, Fairchild made, and everyone else, TI and everyone, made single transistors. They sold individual transistors that were then integrated into electronic systems. But by realizing that when you embed them in the silicon, it's easier to interconnect them within the silicon, that was the dawn of integrated circuits, monolithic integrated circuits. And there were a number of supporting innovations that came along with this. In fact, I'll put a link in the show notes to a talk I gave a couple of months ago that looks at some of these innovations in a bit more detail. But it allowed tremendous benefits because you could parallelize transistor fabrication and interconnect many, many more of them than you would have been able to doing this by hand effectively, right? And so we still use this process today. 60 years, 70 years later, this is the foundation of the semiconductor industry. I have found that it is taken as almost a fundamental law of the universe that this is how you make circuitry. And from my view, we should carefully think about whether this is the only way to make circuitry. Not to take away from the impressive advances and capabilities of a modern integrated circuit and the many technological and societal spaces it has impacted. But to me, it's a process, and it's not a fundamental law of physics. And so we should be very careful assuming it is a fundamental law of physics. And then the last one I'd like to talk about is 3D printing. So this isn't one that has entirely left its mark yet, but it is actively working to leave its mark. And Matthew and I think it's one that's going to be as important as some of these other ones.
Right, and on this one, I think the interesting aspect of how it will change the way we think about manufacturing is it may not be that we make a lot of 3D things that you and I will buy. It may well be that the way it impacts manufacturing is to make the things that make what we buy. So the sort of dies and the tools that we actually use could be 3D printed, and then those will go on to help us make the objects that we want. So, for example, the ability to integrate cooling channels into parts will enable us to make more objects faster, because we'll be able to cool the die back down. Now, there'll be other situations, again, most likely to start with in high-end manufacturing, where we will 3D print. So, for example, the inside of a wheel. So we'll print the hub. And what that will enable us to do is reduce the weight of that hub for the amount of material that is there. And we will do that in the context of aircraft engines, where we may well see the integration of cooling channels with geometries that would be inaccessible without 3D printing, that will allow for us to make lighter, more efficient, higher temperature engines that will deliver more power per unit weight and thereby improve, for example, aircraft efficiency, fuel efficiency. So I can see that, additive manufacturing enables the integration of steps that otherwise would have been very hard to create, and particularly in the areas of part geometry, where without 3D printing you couldn't drill or mold the part to arrive at that geometry.
And the advance and the difference is in this additive piece versus, as Matthew was describing, a drilling process where you drill into a bulk quantity of a part and pull out material. That's a subtractive process. So switching from this subtractive schema to an additive schema opens up these avenues that Matthew's talking about. I remember hearing a talk relatively recently from an HP person talking about the integration of structural and electronic components. Right, so at a 3D printer, you don't have to just print one type of material as you go. You could, as you are building up a component, you put in electronic traces, for example. Maybe you put in transistors. I don't know. But it's the idea that you can, through these additive methods, now think about combining functionalities in a more seamless manner that I think is going to open up entirely new avenues of technology and also research. Right.
And so, for example, here at Georgia Tech, we've been working on how do you print certain polymers. So often we print polymers by melting them, right? But what if you have a polymer in solution? How do you actually print a polymer out of a solution? And so the idea is actually to create a print head where you cause the phase transition from the liquid dissolved polymer to the solid polymer is actually happening as it contacts the object onto which you're printing. And again, this gives you completely new functionality with regards to what you can print, because now you can print polymers with controlled porosity based on exactly how they're coming out of solution, and so you can print structures with gradients of porosity and in fact include other materials like adsorbents in with the polymer as you're printing it, so that you can create gradients of porosity, gradients of adsorbent within the structure that you're actually printing.
Yeah. And so I think it's opportunities like this that suggest 3D printing and additive manufacturing is going to change the way we make a lot of things in the long term, even if today it's still just getting going. I think you gave a great example of the polymers in solution. That's also showing where new science is required, right? That's all driven by 3D printing emerging as a technology, not the other way around. These kinds of phase transformations would have largely been viewed as mundane or uninteresting without the 3D printing.
Right. The other sort of science that connects to 3D printing is mathematics, because suddenly structures that we would have been unable to fabricate without the 3D printing can now be fabricated. So we can make strange geometries, strange topologies that we otherwise couldn't have made, that mathematics has suggested might have interesting properties from a stress-strain perspective, or connectivity of channels, for example. And that's, again, mathematics is being reinvigorated by thinking about how we can now make things that mathematicians otherwise would have left as a sketch on a piece of paper.
Yeah, that's a great example. Okay, so we've given you several of our 7, most of them, in fact. I think we really enjoy those examples, so it was hard not to. But we want to spend a little time now saying, okay, here are several we've talked about. What are some characteristics of each of these that are similar? Because we think there are several that exist. And so the first one is that these fundamental process innovations, these foundational ones, enable a pathway to scale up. So what do we mean by that, Matthew?
So I think in several of the examples we gave from the Watt engine, the Bessemer steel production, the fluidized catalytic cracking, each of those process innovations led very rapidly to the spread of the technology and its scale up. In other words, in the case of the catalytic cracking, you went from cracking 1,000 barrels to being able to crack 300,000 barrels. So there was a very rapid expansion in the capacity of the process, because as soon as you see that you can move the catalyst from one vessel to another, it becomes a matter of, well, how quickly can I move it? How big can I make the vessel? In one of the examples we didn't talk about, once you have the idea of making a sheet of paper continuously, the question is, how wide can you make it? How fast can you have the felt move to pull the paper away from the place where it's being sort of poured onto the strip? And so the pathway to scaling up the technology is almost sort of embarrassingly clear. In the context of computing, embarrassingly parallel almost.
Well, I was going to also say, if you take the planar processing and look at integrated circuits, it just becomes an issue of how small can you make the transistors, how tightly packed can you make them, and also it turns out how perfect can you make them because of the tenets of the planar process. But it's funny to characterize, in my view, the last 60 years of integrated circuit advances as obvious and simple. But in a way, when it's viewed that way, they kind of are. You see the direction that you need to go.
Right, and that's the value of the innovation, because it enables the industry to get behind it and for the scale up to then happen.
So the other thing about these innovations, and this is like any technological innovation, is that they exhibit the so-called S-curve behavior.
So the S-curve is again, so now we've explained how you get the acceleration, but often once the embarrassing part is over, the question is, how do you keep going? And so often you can't. And so the innovation runs out of steam, and you end up in a so-called S-curve, where you have the slow period while the innovation is essentially being discovered. You have the rapid acceleration through scale up, and then you have the essentially just collecting the final part of the efficiency gains you can as the rate of adoption and efficiency improvement plateaus. And so you go through this natural S-curve.
And I think the early stages, right after the initial innovation, is where you get all the naysayers, right? That's where they come out of the woodwork and say that's not going to work. You can look at Bessemer and how the people he licensed his technology to couldn't reproduce it, and they would say this is ridiculous, and they walk away. But once those kinks are worked out, you get past that first inflection point, and you're off in the uptake phase, and that's where it really takes off. And then, of course, it eventually has to end somewhere. I look at the $10 billion cost of a modern integrated circuit fab or manufacturing facility, and there's only 4 companies in the world who can put up the funds to build that thing. And at these costs, their desire to innovate in a meaningful way is, let's be honest, it's not going to be significant. It's going to be very risky. And so we're really, in that case, at the top of the S-curve.
Right.
So, and then there are compounding benefits to these fundamental process innovations.
Yes. So what we saw in the context of the steam engine was that we were able to reduce the size of the steam engine for an amount of delivered power, and that enabled us to move further from the mine and build mobile steam engines, and that has terrific benefits with regards to moving goods and people around. So there were these knock-on benefits that happened there. And then also in the context of Bessemer steel, we're able to control the properties, but because we've removed all the impurities, we can now think about, well, what if I added this? What if I added that? And the clarity you have around the impact is much higher because there's nothing in there that's interfering with the understanding you're gaining as you add nickel or cobalt or other metals. Plus the fact that those metals themselves may well have been purified using exactly that same innovation. So there's a parallel knock-on in terms of adopting it in other industries, as well as enabling you within the industry to actually make innovation. Thinking about paper making again, the innovation of continuous paper making bled over into making rolls of steel, right? You have the same notion of a moving plate that enables you to make a roll of steel.
And I'll add, in the electronic space, the planar process is now used for MEMS to make all sorts of sensors, accelerometers for your cell phone, et cetera. It's used to make the CMOS camera that's in your phone, even though silicon is a pretty disastrous absorber of light. But the planar process and the learning that came from decades of working with it allowed us to make really cost-effective image sensors even out of a pretty bad light-absorbing material. And here's a really important characteristic of fundamental process innovations that we've touched on, is that they themselves catalyze new science. You move in a direction opposite to what most people view as the way technological innovation happens. We talked about fluid catalytic cracking leading people to need to understand how particles move in gas flows. In 3D printing, people needing to understand polymer phase transitions and fluid flow in entirely new ways. Of course, for electronics, understanding diffusion processes, understanding lithographic processes, advanced device physics that probably wouldn't have come if we didn't get really good at planar processing. So instead of from the lab, it's to the lab. And this is one of the characteristics we think is really important to recognize. And of all of these, probably the one that is recognized the least. And actually, we would argue should influence the way we think about the mechanisms by which we fund scientific research. And we can come back to that. And the last characteristic is that fundamental process innovations enable emergent phenomena.
Right. So we touched on this with the steam engine. Again, with this idea that urbanization is enabled by being able to move goods long distances, which the steam engine enabled. And so we have this, now a new organization of the way society can live based on the innovation that came from the process. Bessemer steel, obviously, again, rolled into that, enabled even more efficient transportation. We see now with what effectively electronics have done is to enable, again, a vast range of innovations in society in terms of the way we organize work, the way we organize shopping. These are all phenomena that we wouldn't actually have been able to observe without having made these changes based on process innovations that led to reorganization of activities of society.
So the main reason Matthew and I wanted to write this article was to identify ways to nurture process innovation. And they look different than the usual way we think about nurturing technology, which is often fund fundamental science or fund applied engineering. And I think a lot of these process innovations we've been talking about, really the innovation had to bridge both the science and the engineering at the same time. So we've laid out a few suggestions for how one might think about nurturing process innovation. And the first one is bridging the so-called valley of death. The valley of death is what I just described, which is this gap between fundamental science and applied science, and which has, in my view, become increasingly wide over the last several decades. So what do we mean, Matthew, by wanting to bridge the valley of death?
So I think there the idea is that in many scientific discoveries, the way in which, say, the material that is the subject of the discovery is made is at a lab scale and is made in small quantities, and the researcher goes to lengths to make it in some sense reproducible at that scale. But then, if that is to become something that has an impact outside the lab, we need to be able to scale up its production. And as we described, one of the characteristics of process innovation is precisely this pathway to scale up. And so what we need to be able to focus activities on understanding how to support process innovation that will lead to taking sort of the lab scale production, if you like, to larger scale production, but then to understand how, as we scale up, there are new phenomena that we uncover that we require scientific understanding to be able to continue to move the process forward. And so this is bridging the valley of death.
And it's when you are working on the innovation, there's often, in some sense, you're trying to jam together disciplines that maybe haven't been put together before, or concepts that haven't been put together. And at that interface, new science is needed to meld those two. And so without that science, though, the innovation doesn't happen, right? Then there's the subsequent science that's kind of the knock-on piece, but there's the science that needs to be done to create the innovation. And that's at this interface, right? And so that's really important, I think, to recognize. One way we think we can incentivize people to want to work at this interface on the bridge between the fundamental and applied side is by trying to target grand challenges.
Right. So here the idea again is that if we have factored the fundamental and the applied too much, that we may not be able to work at the interface, but that almost by definition, grand challenges such as healthcare, climate change, and other such challenges require the integration and convergence of disciplines. And so through that focus on a grand challenge, and the idea that whatever has to come out of the activity should address a very important problem, it almost by its nature enables us to have innovation that will carry across the valley of death.
And it's the kind of thing that helps to put into context some of the more incremental work that needs to be done to enable the innovation. It's almost like you're protected as someone working in that space because this is a piece of a grander challenge. And without that, you might be looked at as like, why are you doing that? Right. And having the freedom to say, yeah, it's this thing. I'm not doing that just yet. I have to develop these intermediate pieces is something we don't often afford our colleagues, at least within the academic community. And so it's important to connect to a grand challenge, and then also the flip side, recognize that the grand challenge you're not gonna get there right away. There's these pieces that have to happen on the way there. Another key thing is really be sure you know what to quantify.
Right, so this comes back a little bit to the very start of the show when I talked about the journal, in the sense that we have to understand that we may have become focused on certain metrics of a particular process because those were important to push that innovation forward. But the newer innovation may actually be targeted at a different performance. So we often talk about performance versus cost. And it may be that in the initial phases, you're willing to sacrifice one or the other of those two performance metrics in order that the innovation get going. But then once it starts, it has the ability to drive the other one back down. So that's one of the ways in which we have to be sure not to focus on the metrics we have always employed, but actually be prepared to accept some lesser performance in certain areas.
So Clay Christensen talks about the concept of sustaining and disruptive innovations in his book. And the disruptive innovations usually look inferior along conventional metrics at the outset. And eventually they don't. They get better. But in the early days, you have to be somewhat willing to accept inferiority along one axis if there's a benefit along another. And expect that in the future, that thing that's viewed as inferior will be kind of wiped out by the innovation. I mean, shopping's a great example. You as the customer walking around is inferior to handing your list to the shop clerk. But of course, we get tremendous benefits now from walking around. So you have to be careful about that.
So one of the areas where there's an argument, I think, sort of almost raging at the moment is in the area of education.
Yeah.
Should we, we have the metric of quality of the education, but we also have the metric of access to education. And so online access can provide a much larger audience with the ability to participate in the educational process. But in the early days, we may struggle to maintain the same quality of education as we improve access. And so, again, it may be that we have to wait and figure out how to improve the quality whilst we improve the access.
Yeah, I find it interesting to be at a place like Georgia Tech, which is a phenomenal institution, and you talk to people around campus, and generally the mindset is, online learning, for example, is inferior to what we offer at Georgia Tech. And on the surface of it, of course, I mean, anyone would love to come to a beautiful campus and be able to talk about cutting-edge ideas, but that limits access to many people, and there's many people on the face of this planet who don't have the resources and don't view the quote-unquote quality we provide as critical. They would be very happy with a much lower cost education remotely. And so this is a very interesting time to be on a campus like Georgia Tech, and I think the same can be said for most other research institutions that are out there, that we provide a very high-end product, and not everyone, and there's actually a relatively small fraction of people who can use that high-end product, right? Okay, so two more. Learn when to move on. Easier said than done, I think.
Right, and I think here we would argue that this comes back to the top of the S curve. When does a process innovation actually run out of steam? How do we identify that early enough? And that is really the key question.
Right.
To know that yes, we need to maybe relax the performance requirements and go into a more innovative space to be able to provide the next generation of functionality. And again, if we come back to the sort of silicon manufacturing area, one of the areas you would see that is Moore's law has predicted the continual doubling of density and therefore the lowering of cost. But at some point, the fixed costs of the facility start to become very significant. So even though you're able to drive down the per transistor cost, the fact is there's just so many fixed costs associated with that the overall facility becomes too capital intensive to build.
It's also just challenging because over 50 years, or whatever the time scale for these process innovations, so much has been invested that there are significant sunk costs, significant. And mindsets have been changed, and people's views of the world are set. And so that, potentially more than anything, is why you often get stuck at the end of the S-curve in a bit of a pickle, so to speak.
Right.
And then the last thing is we think there is an opportunity to start thinking about process innovation as a discipline.
Right. So this one. So we're writing the paper, and at the time, I'm obsessed with this notion that we should make this more accessible, and that's really what I would see as process innovation as discipline is. These ideas about parallelizing, factoring, separating, merging, splitting, these schema are actually things that we can teach people to apply to the processes that they engage in on a daily basis. And it doesn't have to be within the context of manufacturing. We all execute processes. We all, well, not all, but most of us cook. Most of us travel to and from work. We engage in processes with multiple steps, and how we can organize and change the way we execute those steps is really something that could be of broad benefit across a wide range of disciplines.
You made me think of Uber and Lyft are process innovations in the transportation space.
Exactly. And it seems to me that as a society we could become more innovative if we were to consider how individually we could influence the processes that we're engaged in and around us. Banking, finance, management processes. These are all processes that we execute, and being more intentional about the way we design and innovate around those processes is something we could do with some help with. And I think that's where a discipline of process innovation could see its niche.
So that's about it. That's your kind of not necessarily sneak peek. That's a nice long overview of what we put together, and we're hoping it gets published here in the coming months. And we hope it gives people a lot to think about, and we hope a lot of different kinds of people read it. I mean, I think nanotechnology, nanoscience, or the translation, or taking nanoscience and actually making it impactful in people's lives is going to require process innovation. We've talked about some of those ideas on the show before. Separating components, like we separate molecules from a mixture of cracked crude oil, right? These kinds of things, I think, are going to be absolutely essential for nanotechnology to ultimately make its mark, and it will. But we're kind of a bit stuck in a rut, I think, at the moment. So that's a piece of what motivated me to engage with Matthew on this topic. And Matthew has an even broader perspective than I do in processing, because of his background in systems engineering. And we will see how people view this. And if you have feedback, we'd love to hear from you. So write in, send me a note on Twitter, whatever, and we'd love to discuss this further. So with that, Matthew, thanks so much for your time.
Thank you very much, Mike.
You've been listening to Nanovation. If you enjoyed the show, please leave a rating or write a review on Apple Podcasts. Show notes are available at fillerlab.com/nanovation. Nanovation is recorded in the Marcus Nanotechnology Building on the campus of Georgia Tech. Andrew Cannon edits the show. I'm Mike Filler. See you next time.